The position time graph we will discuss in this installment. If we look at the normal coordinate plane, quadrants 1, 2, 3, and 4, since we are now, an object is starting at 0, since the object is starting at 0, the graph will be located in quadrant 4. And quadrant 4 is where the positions are negative and the times are positive. So it's located in quadrant 4. And so this looks like what we saw with horizontal acceleration. It's a parabola. And we can see the fit here in this equation, which we'll talk about in the next installment. But if we were to look at the projection of the points to the vertical axis, so if we project this point backwards and make a point right there, and project this point onto the axis, and this one onto the axis, and this one onto the axis, and this one, and this one. You may remember that we discussed that when we project these points backward, this becomes the motion dot diagram. And what these are showing, of course, is the delta z's. We can see that as the object falls, downward, the delta z's are getting larger. And that ends up producing a parabola shape. Now, we could say, when we describe this shape, we call it a downward cupped parabola. Because up until now, we've seen the parabola of an accelerated object looking like this, and that's where the positions are positive and the times are positive. And what we're looking at when we're dropping this thing is we're looking at where the positions are negative and the times are positive. So that makes the parabola cupped downward like so. But it's a parabola nonetheless. And of course, if we extended it all the way, that parabola would look like this and the other one would look like this. But remember, these are negative times on this side of the z-axis. So we're only concerned about the time that's progressing forward. So it's only this half of the parabola. But we will also notice, if we look at this position time graph, if we look at the slope, which is delta y over delta x, the y-axis is z, so it's delta z, and the x-axis is time, so it's delta z over delta t, meters per second. Just like every other position time graph, the slope is the velocity. And we can see this is a very flat slope. Here we're getting a bigger slope. And the slope is getting more here. Like so. And we also, since the slope is pointing in this direction, all the slopes are negative. The slopes are negative. But you can also see that the slope is increasing, therefore it's accelerating. And we saw that previously, that on a position time graph, if the slope is changing, in other words, if it's curved, then there is acceleration.